Welcome to this tutorial, which is going to look at another aspect of shading, which is creating your own Illuminance model using an Illuminance loop. I've got a simple scene set up here illuminated by distant light, and I've got a camera set up, and I'm going to zoom in the camera so that we're focusing on the sphere. And if I render that, we see that the sphere has a shadow cast on it, and we'll see why that's important a bit later on. And I've created here an empty material with a box surface shader attached, and at the moment I've done nothing else to it. So what I'm going to do is create my own Illuminance model. Now, as we saw in the last set of tutorials, Houdini comes with a number of default Illuminance models. Some of them are in this lighting model node, and that gives you things like constant, Lambertian, Oraniah, Phong, Blinn, Specular, and so on. And there's also a separate node for Lambert and a separate node for Oraniah. But what happens if these particular models that are built into Houdini don't capture the effect that you want? Well, you can in fact create your own lighting model. But before we do that, a word of warning. This only works with the standard mantra renderers. You can't create your own lighting model with the PBR renderer. You have to use the built-in models for that, which are reasonably well documented in the Houdini documentation. So let's start by laying down an Illuminance loop node. An Illuminance loop node has inputs for the position, so let's connect that, and for the normal. And I'm going to normalize my normal so that it's of unit length, and we'll feed that in. And then it has an entry for the angle, and this is the angle over which it will search for lights. So it compares the light vector, the vector from the micropolygon we're shading to the light, to the normal from the micropolygon, and if the angle is within this angle here, then it considers it within the Illuminance loop. So for this I'm going to create a constant, and I'm going to give it a value of 90 degrees, or pi over 2, which is pretty much what you always want. These extra parameters down here, the light type allows you to set this Illuminance loop so that it only takes into account diffuse lights or specular lights and so on. By default it takes into account all lights. And the light mask control here allows you to mask out certain lights by name, and as you know, that masking capability is available also on the lights themselves, so it's usually better to achieve that using the lights themselves rather than here in the shader. You also need to input into the Illuminance loop any variables that you're going to need inside it. And I'm going to need the I variable, and as you remember, I is the vector from the camera to the micropolygon. So in this case I'm going to take this and I'm going to negate it, and that means I'm going to get the vector from the micropolygon to the eye, to the camera rather than vice versa, and I'm going to normalize it so that it's unit length. And then I'm going to feed it here into the next, and as you can see, as soon as I did that, this is added and we get another next parameter. Now what an Illuminance loop is a loop that loops over all of the lights which illuminate the micropolygon we're shading, and it executes the code that we'll put inside here once for every single light. So let's dive inside. And the example I'm going to demonstrate today is part of a Velvet shader, and it's based on a shader developed for RenderMan by Stephen Westin. And if you look at the renderman.org site, you can find the source code for it there. So let's lay down a global variables node, and we get two global variables in addition to the normal ones inside when we're inside an Illuminance loop, and those are CL, which is the color of the light we're currently processing, and L, which is the vector from the surface to the light source. And note that in the diagram that I showed in the earlier series of surface shader videos, the arrow for L is pointing in the wrong direction. In the diagram it points from the light to the surface, and in fact it's the other way around. So let's change this so that it outputs a single variable, and I'm going to output the direction, the vector from the surface to the light, and then I'm going to normalize that. And I'm going to take a dot product. I'm going to take a dot product of the normal and nvec. Nvec, if you remember, is in fact the negated I variable. And I'm going to take the dot product and I'm going to clamp it between 0 and 1 so that I don't ever get any negative values, and by default the clamp node operates between 0 and 1. And I'm going to square this by using a multiply node, and then I'm going to subtract it from 1 using a complement node. The next thing I'm going to do is take our normalized light vector, and I'm going to take a dot product of that with our normal, and then I'm going to multiply the dot product here by the result of this calculation, except that there's a further step, which is I'm going to take the square root of this value and then feed that in. And we're going to need to multiply this by some other factors, one of which is going to be the color of the light. So let's take the light color and put that in here. We see we're getting an error here because we've tried to multiply the float values first and the color last. So if I bring up a parameters plane, look at the multiply node, we need to make sure that the color is the first input, and then this works fine. And in fact there's another couple of steps here which are going to need me to create some parameters that are going to influence what happens inside this node. So I've set up two parameters. One of them is a float parameter with a default value of 10, and the other one is a color parameter, sheen, which is the equivalent of the specular color for the purposes of this Illuminance model. And that has a default value of white. So we can just connect these in here and go back into our Illuminance loop. And the steps I'm going to use are to take a power function, and we're going to take the square root value, and we're going to raise it to the power of edginess, which is one of our parameters. And then this is going to go in to our multiply node. Finally, we're going to multiply the whole lot by sheen, which is our color. And that's the end of this component of the shader. So what do we do in order to get the value out of here? Well, we can't just connect this product to anything here. We're going to need to create a variable rather, in which we can store the accumulated color contribution of all the lights as they are looped through using the Illuminance loop. And to do that, we need to create a constant, and despite its name a constant, can serve as a variable in which to store. So we're going to call it total color, and it's going to be a color, and it's going to start with a value of 0, which is what it starts with by default. Let's make this a purple color, and we connect this into our Illuminance loop. And what we want to do with this is bring it in and use an add node to add this and the contribution from the current light. And then we take the sum, i.e. the result of this addition, and we feed it back in to the total color connector on the output node. And what this does is ensure that the value of total color is fed back in every time the loop iterates. So we start with a total color of 0, then the contribution from the first light is added in, and that produces a color. That color is then fed back into our loop for the next iteration. The light contribution of the next light is calculated, that is added in, and so on. So once the loop has iterated through all the lights, we will get an output here which represents the total illuminance according to this illuminance model. And we're going to feed that in to our output node here. See what that looks like when we render it. So I'll go up to the shop level and I'll put this onto our sphere. As we see, we get this sort of velvet-like effect where the light is strongest around the outside of our sphere, and it's a bit brighter when the sphere is nearer the light on this side than on this side over here. But what we're not getting is any shadowing. That's disappeared. And the reason for that is that, unlike, say, in RenderMan, shadows are calculated inside your surface shader, and we need to add something in to our Illuminance loop to do that. And we need to do this by laying down a shadow node. And the shadow node will calculate shadows according to the settings on our light. And the light color goes into one side of the node, and we use the color that comes out instead of our light color, because this will take into account shadows. So what we should see, if we now render this again, is that we're getting the shadow reflected here on our scene. So that's an illustration of how to set up an Illuminance loop inside a mantra shader. And in fact, this Velvet shader, the Stephen Weston shader, has a separate another component, and then you need to add in diffuse and ambient shading and take account of opacity and so on. I'm not going to demonstrate that in the video because it's essentially the same process that we used in the earlier shader videos, but in the downloadable file you will get the complete shader. So that's how to use an Illuminance loop, and I hope it's been useful.